Today we're going to talk about cardinality, or size of sets. Before now, we've only focused on finite sets, but now we're going to talk about infinite sets. Let's first make a definition. We're going to denote the cardinality of a set A by A with lines around it, just like we did for finite sets. And we're going to make a few definitions. We say that A and B have the same cardinality, or their cardinalities are equal, if there exists a bijection from one set to the other. We say that the cardinality of A is less than or equal to the cardinality of B if there exists an injection from A to B. And finally, we say that the cardinality of A is strictly less than the cardinality of B if two things are true. The cardinality of A is less than or equal to the cardinality of B, and they have not equal cardinalities. In particular, this means there exists an injection from A to B, but there does not exist a bijection from A to B. Now let's consider the following relation on sets. We say that the set A is related to the set B if they have the same cardinality. It turns out that this is an equivalence relation, and we'll go through the details below. Some definitions. We say that A is countably infinite if the cardinality of A is equal to the cardinality of the natural numbers. We say that A is countable if A is countably infinite or if it's finite. We will also use the symbol aleph null to represent the cardinality of the natural numbers. Now a theorem. A set A is countable if and only if it can be put into a list. See here for details. In particular, we could also use the word listable instead of the word countable. Now we're going to show a couple of results. We will first show that the even natural numbers have the same cardinality as the natural numbers. And we will also show that the integers have the same cardinality as the natural numbers. In particular, this means that each of these sets is countable. Okay, here's a nice result. We're going to show that the rational numbers are countable, or that the cardinality of the rationals is the same as the cardinality of the naturals. In fact, we're going to prove this as a corollary of a more powerful theorem, which tells us that if we have a collection of countable sets indexed by the natural numbers, then their union is also countable. We also have a couple of nice corollaries from this. We can show that the set of pairs of natural numbers, sometimes written as n cross n or even n squared, is countable. We can generalize this idea that if we look at vectors of length p, where the entries are natural numbers, this set of vectors also forms a countable set.